UAA Robotics is proud to submit our system acceptance review video for consideration by the 2021 University Rover Challenge Judges Panel. This year has posed many challenges in the continuation and development of our Mars rover and team as a whole due to the COVID-19 pandemic. As such, we were urged to address our SAR as a 2-year project lifecycle. Entering our 5th year with support from UAA and many professional and private organizations, our team of over 10 students chose to iterate upon and optimize last year's design. We proudly present Iceberg 4. UAA Robotics is divided into teams dedicated to each rover subsystem: mechanical, electrical, software, science, and project management. We updated our Gantt chart and task lists based on challenge requirements and available resources. By utilizing FEA on mechanical structures, 3D printing, industrial machining equipment, and computer programming frameworks, we rapidly prototyped and optimized new designs and refurbished old ones. As supplies were purchased, we built, troubleshot, and tested systems in parallel.
The Iceberg 3.5 chassis was designed around the extreme retrieval task and remains largely unchanged from last year. It consists of a main structural member cut from 2-inch square tubing that runs the length of the chassis and 2 custom C-channel beams that contain suspension elements. This led to a very simple yet effective design.
The rover runs on a 720 watt-hour lithium-ion battery pack, providing ample power for each competition task. 5 cameras face in various directions to give the driver sufficient visibility at all times. These provide multiple close-ups of the end effector and wide-angle views of the arm and rover. The rover uses a set of 900 MHz ubiquity radios to provide multiple video streams as well as rover commands, allowing maximum propagation across terrain. A pair of 5 dBi dipole antennas are mounted high on the rover, while the base station uses a 120-degree directional antenna with a 13 decibel gain.
The base station runs a custom graphical application built with WX-Python for viewing rover camera streams and monitoring and controlling the rover. It utilizes a navigation system to display the position of the rover in real time from transmitted GPS coordinates and a configurable control system, enabling operation of the rover with a pair of gamepad controllers.
Due to inaccessibility of our innovation lab, we focused heavily on improving our computer vision, object recognition, and navigation software for the autonomous traversal mission. During navigation, the rover uses an onboard GPS and accelerometer magnetometer to precisely determine its position and orientation. The OpenCV and scikit-learn Python libraries, as well as the TensorFlow machine learning framework, are used to analyze the image and depth data from a stereoscopic camera to detect obstacles in hazardous terrain and identify competition markers. Our Pathfinding system uses a record of data from encountered obstacles, as well as unsupervised machine learning algorithms run on an NVIDIA RTX 2070 graphical processing unit to calculate the most direct path to waypoint coordinates. We use these data and models to train a convolutional neural network to aid the rover to better identify key competition objects and avert potential hazards.
The arm design drew inspiration from a number of industrial sources. The shoulder is powered by a 200-pound linear actuator, minimizing any moment forces in the upper arm. The elbow uses a 30-to-1 worm gear transmission that provides smooth, predictable motion and over 100 pound-feet of available torque. This design allows the forearm to be offset from the upper arm to gain 360 degrees of freedom. We elected to use a worm gear on the wrist along with a unique end effector design that is able to rotate continuously without the use of slip rings.
The end effector utilizes a gripper and screwdriver system to accomplish the extreme retrieval and equipment servicing tasks. 3 DC motors and a linear actuator provide a clamping force of 13 pound-feet in a range of 2.5 inches with precision control of 0.09 of an inch. Paired with the robotic arm, the end effector has a 5-axis range of motion. The main axis is controlled via a worm drive gearbox minimizing power draw. A 3D printed enclosure prevents dust from entering the gearbox and belt drive systems.
The science plan encompasses a combined approach that includes visual observations, an array of sensors, and wet lab chemistry to identify signs of life. A camera scans the area for the presence of animals, metabolic wastes, tracks, microbial mats, iron staining on surfaces due to microbial metabolic activities, and fossils. Soil and mineral samples are analyzed with a variety of sensors and a computer program that uses Arduino and C+ libraries, including spectroscopy and gas detection algorithms. The samples are then added to a luminol mixture to observe luminescence levels to determine the presence of oxidizers, including hemoglobin, protein, urine, feces, copper, or iron.
This concludes our 2021 SAR video submittal. We appreciate your consideration and look forward to seeing you at the Mars Desert Research Station this summer. Thank you.